much for the very nice introduction. Also, thank you very much for the invitation. It's really a great pleasure for me to be here. Now, I think we all know how tremendously successful AI is these days, but at the same time, we are also aware that there are still major problems. In particular concerning, and this we already heard to a certain extent in the last talk, safety, in particular in general, trustworthiness. But then there's also another main problem which we encounter with AI, which is sustainability. And so in this talk, I would like to take a more, I say, foundational approach towards these problems, and you will see that in a very natural way, this will lead us to what we can call next generation AI computing. So, I think we all know that we are at the beginning of the fourth industrial revolution by artificial intelligence. We see our lives changing around us on a daily basis. We already heard about self-driving cars, robotics, telecommunication. Very sensitive areas are also already touched, like the whole legal system, the job market, and then I myself come from sciences. There's not one area in the sciences which has not witnessed a paradigm change by AI yet. And if we look into the future, we are expecting, as it is the case with every industrial revolution, which we had already, this is now the fourth, we are expecting a radical change of our society in its full breadth. And again, I mean, every new technology comes with pros and with cons. And as I said, one of the problems we are still encounter is reliability and in general trustworthiness. So here are a couple of examples. The first, we already heard an amazing talk just, a couple of minutes ago, problems with safety. We have still accidents with robots, and a self-driving car is nothing else than a robot. We have problems with security. One can hack into those systems, modifying things slightly so that an AI would make a radically wrong decision, but a human would not recognize the difference. These methods are also very data hungry. And we have privacy violations happen on a daily basis worldwide to collect that kind of data which we need. And also problems with what I might say responsibility. So many of these decisions are black box decisions. We don't really know how the decision is taken, and also decisions can be biased. So in that sense, I think it's fair to say that one current major problem worldwide is the lack of trustworthiness of AI technology. And what I would also like to show you is, if you understand things from their depths, and here I would like to also advocate then that from the depths also means from a theoretical, from a mathematical viewpoint, then you can see where the problem is and you can also tackle it. The second main problem, which I already discussed briefly, is sustainability. And with sustainability here, I mean energy efficiency. You might have seen this on Twitter or X if you're on social media. So Oracle is building the new hyperscaler in the US, and they are planning the 3 nuclear power plants which should provide enough energy right next to it. So this already shows the seriousness of the problem, of the energy problem which AI causes. But the situation is even more serious. So here I brought you the figure from the decadal plan of the Semiconductor Research Corporation for the Biden administration. What you see plotted here is the world energy production over time. The world produces more and more energy. You see that here. And I would like to show you now the curve of the energy we just need for communication, also communication between AI agents and so on, but just for communication. And this is how it looks like. And you see the problem, because we cannot use more energy than the world produces. So if there's a limit, this is it. Now, if you see on the right-hand side, this is with CPUs. If we change the hardware a little bit, we can make things a little bit better. This crossing point, we can move to the future. If we use new platforms like new hardware, we can lower it even further. And then if you're also smart and also consider the software, and bring in also theoretical mathematical aspects, so in this case, it's this new post-Shannon theory, we can lower the curve even further. But still, I think, from my viewpoint, the message here is we cannot continue the way we do right now. We cannot scale it up more and more. So on the like you see on the left-hand side, we need disruptive new ideas to tackle the energy problem, but also the reliability problem. And so in my talk here, I would like to take a foundational approach, and I would like to show you where this leads us. Okay, so let's take a mathematical perspective. AI is nothing new. It's actually quite old. It's from 1943. So at that point, McCulloch and Pitts wanted to introduce artificial intelligence. And, well, I mean, we humans, we believe we are smart and intelligent, I guess. I mean, if I would ask any one of you, you would say that's true. And so what they did was they mimicked the human brain. The human brain consists of neurons which are interconnected. And so what you see here is a mathematical model for an artificial neuron. So you see these XIs, which are the incoming signals. They're amplified by the weights, and then the neuron sends out another signal. And so now we connect all that to an artificial neural network, which is this. Yeah? So, I mean, I don't want to go into the details, and believe me, I think these are the only formulas in the whole talk. But I would like to show this to you once to make clear that AI, in a sense, is mathematics. Yeah, it's a mathematical function. So in that sense, I mean, we have all the tools from different areas of theory available to tackle that, to analyze that, to make it more rigorous. So now I would like to show you what the, let's say, key directions are where people are aiming to get a hand on first reliability and trustworthiness from a foundation. And for that, I would like to take you once again to the workflow, how you apply neural networks. I'm sure most of you or any of you knows that, but let me just take that step. So what do? You have something complicated you want to learn, a complicated function. You have images, usually, I mean, in this case, cats and dogs, which you would like to classify, and each of those has a limit. So you split this into training and a test data set. You have to choose the architecture, which is already, as I guess everyone knows, a lot of trial and error. So we have to test different architectures, which ones works best. We have to train. So that means learning the weights and the biases. There's a very classical algorithm which does it for us, and it's basically moving over a very complicated landscape, finding a good minimum. And finally, I mean, the performance check, whether what we have learned is something which is reasonable in the sense that if you now apply it to unknown data, it works fairly well. And so from that, I mean, also what people aim for now for trustworthy AI is driven. I mean, there is the question which architecture to choose. Yeah, and that costs also a lot of time, a lot of money, because people try different architectures in parallel, therefore you need these big clusters. But if you would have guidelines, that would be much better. That's the area of expressivity. Then the training. So can we speed up the training in a certain sense? Can we use additional features maybe of the data? So that's the second direction, learning. And then comes what people sometimes call the holy grail of AI theory, which is generalization. So can we understand the performance on unknown data? And that's what's also typically related to safety, because we would like to have rigorous error bounds. And then there's another area which is also, I think, extremely important these days, which is explainability. And so tomorrow you will hear I think, a keynote talk by Ludwig-Maximilians-Universität on explainability, because now you would like to understand how decisions are reached. So let me first make a short dive into generalization to show you a bit what I mean in that direction. So the big question overall is, why is the larger the better? So if you ask people what network to take, well, take the largest, which still fits in your GPU, and hopefully you can analyze also the generalization error. This effect you see here in this figure, maybe you've also seen the figure. So what you see here, this capacity, that's the size of the neural network, then the risk is the error. And what you see here, this dotted line is the training error. So certainly if the network goes larger and larger, the network, well, I mean, accustoms the data better and better. So the training error goes down, but the test error goes up again. So that's here the overfitting. But if you now continue enlarging your network, if you go to this modern regime, then the test error goes down again. And so this is a phenomenon which is still not completely understood. And I would like to show you one result which shows, I think, the direction we need to go here. And this is for graph neural networks, which is also a very hot topic. So we have many types of data which are not just normal Euclidean numbers, but which are graphs. You see some applications here, recommender systems, fake news detection, chemistry, and so on and so on. And so a graph is just, I mean, A graph signal is just a graph where each graph node is associated with, as you see here, a feature vector. So now, I mean, you can ask, I mean, can I get, let's say, my hand on how my graph neural network performs on unseen data? And so you can take two graphs and you can say, well, one is maybe in my training data set, the other in my test data set. Can I estimate the error? And so what we did there was, I mean, we looked at graphs which are somehow alike, which are maybe similar molecules in a certain sense. And we can ask the sub-question of what's called transferability. So let's say my figure or my graph on the right-hand side is in my training set, the other's in the test data set. Can I understand how good my network, which is trained on the training data set, performed on the test data set? And so you can make this precise. And the main point I would like to make here is you can get very precise error bounds. So we can estimate the generalization error in this case very precisely by, and I mean, I don't want to go into the details as said. I mean, this transferability error of the graph, Laplacian, and so on. This is just a very precise error bound which gives us safety and stability. And so this is what I mean when I say mathematics ensures, in that sense, trustworthiness of AI by giving precise error bounds. And so for critical infrastructure, that's absolutely, as it says, critical, because otherwise you cannot guarantee that the AI does what it should. And then you have also the problems which you saw in the previous talk. So now, let's also ask, I mean, what is maybe the core of this problem? And this will also lead us to this problem of sustainability. So the core of everything, which we do also in AI, is in fact the computing. And that's not that much talked about. Everybody talks about algorithms, optimizing algorithms, making the software better. But in fact, I mean, the core, we need to dig deeper. The core is actually the compute. And we don't much ask whether the compute itself causes problems. So maybe this is the problem. And so computing, in our century, computing is at the heart of any modern technology. But if you look closer, we always use digital hardware. So we break our problems, whatever they are. Maybe they are also kind of continuous time problem. We break it down to zeros and ones. And so the question is, does this cause, because of this approximation, any issues which we might not visibly observe, but which are lurking in the background and then lead to all those problems which we observe? Reliability, trustworthiness, and also energy efficiency. And so we ask ourselves, I mean, what can you actually compute on digital hardware? I mean, that's in a certain sense the core. If you cannot compute something correctly, then this causes certainly trustworthiness problems, and it could also lead, in a certain sense, to energy efficiency problems. And so there's a beautiful theory, which is computability theory. Again, I don't want to bore you with the details, but you can make this all very precise mathematically. And if something is not computable, well, I mean, you can still put it in your machine, something will come out, but certainly you don't have any guarantee for correctness or any guarantee concerning safety and reliability. And so, unfortunately, I mean, what we could show, and this is also backed up by several other international colleagues, certain problems, so here, so-called inverse problems, so where you have, say, some measurements and you would like to invert, like for instance, for computed tomography, is not computable by a neural network. So that doesn't mean it's always wrong, but it means there could be some instances where a wrong answer is given. And so this is something certainly, I mean, which is something we should know, and maybe this is a problem also for some of the trustworthiness and reliability problems which we observe. And so let me just show you, I mean, you can make this concrete, don't look too much at the details, but you can formulate that, I mean, very clearly, and you can get a very precise result in this direction. Okay, that's actually bad, and also kind of disappointing, I guess, to a certain extent. So in that sense, digital hardware actually pushes us towards this path. Yeah, so it's maybe also software to a certain extent, but the hardware, the core, this is one of the main problems. And so the question is what to do. And so also, we again, did a deep dive into theory, and so what we could show is that things become computable if you go to analog hardware. Yeah? And so there are also mathematical models. Again, I don't want to bore you with the details. Yeah? So the digital machine, these are Turing machines, and then there are models for also the analog machines. But this shows that, if you want to have trustworthiness, reliability, you need to also consider novel hardware. And interestingly enough, there are exciting developments right now concerning novel hardware. You might have heard of neuromorphic computing. There are various companies internationally, IBM, Intel, Spinnaker, and so on and so on. All of those produce already neuromorphic chips. There's biocomputing. People have living neurons and they aim to compute in these neurons. Quantum computing, I guess everybody has at least heard of. Yeah, so all of those are developments concerning analog computing, so new types of computing. And interestingly enough, if you look closely, neuromorphic computing is also much more energy efficient. Yeah, quantum computing will not solve the energy problem. That needs a huge amount of energy. But neuromorphic computing seems to go in the right direction. And so the hope is to get trustworthy and also sustainable AI by next generation AI computing, by embracing novel types of hardware, like, for instance, neuromorphic computing. And we also just founded a company, Ecologic Computing, in this direction, which embraces this phenomena. So let's now, in the last minutes, look a bit closer at this neuromorphic computing to show you so that you see what the ideas are in that direction, why it might be more energy efficient. So neuromorphic computing, so this shows, first of all, what you see here. Yeah, so this is this Spinnaker neuromorphic computing. You see here that it is much more energy efficient than normal computing, and also it is in certain ranges much more, let's say, successful. Yeah, and so right now, if you have a laptop in front of you, some have, yeah, so this is what you have in front of you, the von Neumann hardware, the classical architecture. We had split everything to zeros and ones. The neuromorphic architecture is very different. It kind of aims to mimic the human brain. So the human brain, again, consists of these neurons, which are interconnected. And so this is what the neuromorphic architecture aims to mimic. Yeah, and so our human brain is an amazing computer. First of all, it uses not a huge amount of energy, just 20 watt, which is, tiny compared to all these GPUs. But it's even not better than that. So, yeah, if you have your laptop or your computer at home, and if something happens, it got stuck, what do? You turn it off, and you turn it on again. Now imagine you would do that with your brain computer. That would be devastating, wouldn't it? So your brain, can kind of wriggle around the problems and solve them, in a sense, on the fly because of this analog structure. So therefore, the human brain is energy efficient, and it is also very flexible and robust. Yeah, and so this neuromorphic hardware is closer to the human brain. It is much more energy efficient. It is also considered a bit higher execution speed, and also concerning robustness, significant advantage. And so we talked about classical neural network. For neuromorphic hardware, we have so-called spiking neural network. So that's a bit more complicated. It's closer to the human brain, because in your human brain, you also don't have any layers of neurons which are synchronized. Every neuron acts on its own, and that's what the spiking neural network actually does. Yeah, so here, what you see here, if you have one of the neurons, it gets input from different other neurons, and it's building up a potential. And at some point, it reaches the threshold, and then it fires. So it's much closer to the human brain, much more biologically realistic. But I mean, so from a mathematical viewpoint, it's also much more complicated. But time is a crucial factor, and time doesn't cost any energy. Yeah, so in that sense, I mean, it has many advantages, I mean, which also visibly you can see that it should be much more energy efficient. And so, I mean, from my, let's say, perspective, and also from my group, we have now also many results which show to a certain extent that these spiking neural networks are indeed much more energy efficient. And let me say, I mean, we have here in Bavaria a large-scale project which I'm leading. It's between Bavaria and Saxony. So these are two states of Germany, the project Next Generation AI Computing. And so the goal is to develop green AI systems, so embracing also novel hardware, novel software, bringing it together to get systems, AI systems, which are maximally energy efficient, but also reliable and trustworthy. And then, I mean, apply it to different settings, like in particular, communication, medicine, and also robotics. Robotics in particular, because you think if you use robotics, a robot for a rescue mission, then certainly you don't want that, I mean, it just gets stuck because it doesn't have any more enough energy. Yeah, so I mean, energy is also a huge problem in robotics, and so this, to our hope, will also to a certain extent solve this problem. And another aspect of this project, which is also, I mean, dear to my heart, is because right now I think we have this community of people who develop software. And on the other hand, we have this community of people who develop novel AI chips and novel hardware. But what is really necessary to do it as a co-evolution of soft and hardware and not separate. And so this is also the core of this project, which we aim for to do, so that goes hand in hand. And I'm very grateful to my team at LMU to support me on that. And so now coming back again to the figure which I showed in the beginning, my hope and my goal is next generation AI computing for a trustworthy and sustainable future. In that sense, also rethinking intelligence. And so we do that from foundational principles. And with this, I'd like to close, and thanks a lot for your attention.
So, ladies and gentlemen, let's hear your questions. We're gonna take 2 maximum. So use this opportunity. And also, I wanna approach the online audience. Please submit your questions to the Zoom chat. We're gonna take those as well if you do. So 2 questions, very quickly, 2 hands shot up. 2 gentlemen over there. Anybody else? Okay, there are 2 others. I promised the gentleman actually in the front that I'm going to take his question. Is that okay? Because I didn't take it. And then we're going to take 1 more, okay? Just given the time restrictions. But let's hear it from the gentleman over here. Good morning.
Good morning.
Take a mic. Yeah.
Thank you very much for your excellent talk. And for the excellent talk of the first...
he's sitting there.
Yeah.
The professor over there, Mario.
My question is about what could be the state, or what could be the result of such work if the state of mood and emotion of the person who conceive and execute this computing is negative, neutral, or positive. So it should be maybe change the things or not, or...
So if we consider human emotions, negative or positive?
The person who will compute.
Okay.
Yeah. Now is in a negative state. Mm-hmm. Tomorrow maybe neutral, and after maybe
okay.
Positive.
Yeah, thank you very much for the question. Very interesting. So I think in general, I mean, if you have a system in front of you, I mean, it should initially be independent on your particular mood, but certainly, I mean, as we get closer, let's say, and it was interesting, I mean, let me just tell you a short story. I mean, I gave a talk in one church. There were a lot of, let's say, also older people, and a very old lady, 80 years old, she said, oh, maybe in 10 years we have a chip all in our brain, which is connected to something like ChatGPT, and we kind of merge our thoughts with a large language model. Yeah, so I mean, if that's the case, I mean, then certainly our mood is very important. Yeah, and so we kind of fuse it with the AI in a certain sense. But I think right now, I mean, it's a bit still independent. I mean, for the future, I mean, it could be as we get, let's say, closer to artificial intelligence and have a direct connection to it. I mean, then we might also be able to influence, or we might also unintentionally influence the AI in that direction.
Thank you so much, and thank you for the question. Okay, one more. There were two gentlemen over there, one over there. So, please, who's going to be the gentleman and give a word to? You want to ask the question? The other two gentlemen, are you okay with that? Okay, so I'm just going to give it over there. I don't want to cause any hard feelings over here. Fine.
Sorry for taking over again. Yeah, I have a question regarding your explanation about the human brain and the spikes. So you have shown us, let's say, a function like a threshold, a ReLU function. My question is now how we can include such an activation function in an analog network like an optical neural network.
Thank you.
So I think you refer to the figure I had with the potential which builds up. I mean, so the potential itself is an analog function. And so, I mean, so this is thresholding you can also implement in analog hardware. But I should be fair and say the neuromorphic hardware we see right now is not completely analog. Yeah, so there are a lot of, let's say, digital elements. But, I mean, we are cooperating with a lot of startups in the area of Dresden, which is kind of the microelectronic hub of Europe. And so there are a lot of startups which go in the direction of, I mean, really truly analog hardware. And this is one thing. The other thing I should say is what I showed you. I mean, this neuromorphic hardware and spiking networks, it's not completely the human brain. It's one step closer. But from my perspective, what also needs to happen is that, I mean, mathematics, in particular also computer science, should work more closely with neuroscience, I mean, to drive this direction further.
Perfect. Well, thank you so much. Please, ladies and gentlemen, a big round of applause for the professor. Thank you so much for an excellent question and a great Q&A.